the universe has been around long enough that everything has been entangled with everything else.
And this idea of entanglement, just so I'm sure I know the whole story, we're talking about the fact that this whole point about spin and when two particles that were joined together are separated by any distance, it doesn't matter, that if you change the direction of spin on one, it will automatically change the other one? Is that the point of entanglement, or is there a lot more to it?
It's probably much more fundamental than that. Okay. What you just described is one of the first ways of testing.
Was that the Einstein-Podolsky?
Well, they wrote an article saying that it couldn't be done.
Okay.
And then John Bell in 1964, I think, wrote a theorem saying that if quantum mechanics is true, then you would end up with this strange result.
Okay.
And in 1982, it was experimentally tested, and has been tested many times since then, and quantum mechanics holds. So back in the 30s, when they were all discussing this idea of entanglement, which Schrödinger, he was the first to use that term. As he put it, that entanglement was not a property of quantum mechanics, it was the property of quantum mechanics that made it strange from the point of view of classical common sense. That things were connected even though they weren't near each other. So what it did was it changed three fundamental assumptions about common sense, which is formalized in classical physics. One is that space and time are absolute. They're sort of given out there. We look out in the world and things look pretty stable, and our clock keeps ticking pretty much the same way. And so Newton and Aristotle way before him simply gave as given that space and time are absolute. So relativity came along and got rid of the absoluteness of it. Quantum mechanics comes along, and at that level, quantum mechanics, space and time are completely transcended. Both.
Mm-hmm.
An entangled pair of particles, and now we have, by the way, trillions of entangled particles in a laboratory for long periods of time and at room temperature. So as you read this in my Shift article about how the progression is going from very abstract single particle and two particle systems that are very rapidly being extended into larger and larger systems, which I would predict will eventually go into bioentanglement.
Mm-hmm.
But that's getting ahead of the story.
Okay.
The classical world, you have three characteristics. It's locality, reality, and causality. Those are the three components of what we mean by a classical world. Reality is, I guess it doesn't matter which one. Reality is that you assume that when you don't look at the moon that the moon is still there.
Mm-hmm.
Assume that there is a given world that is real, it's out there, it's independent of us. Locality is the assumption that the only way that something can happen is if some kind of force is exchanged between two things,
mm-hmm.
two or more things. So it requires a contiguous contact state at some point. Things have to impinge on each other. And the third is causality, where you can only have cause and effect, and that sequence can't be violated. So sometimes you'll hear about people who don't like psi because it violates what they call basic limiting principles in science. What they mean by that are locality, reality, and causality, which is classical physics.
Right.
Relativistic physics got rid of causality in its usual sense, and it got rid of not locality so much, but reality is put somewhat into question, but mainly it really questions the absoluteness of space and time, and that puts into question causality. Quantum mechanics has gotten rid of locality completely. We now know that at some deep level, the world is non-local, meaning that it transcends space and time, which means that it's not causal. And worse than that, it also means that the sense of reality that we have with common sense also is no longer true. If you don't look at the moon, it is not there. It's not there in the sense of what we think of as the moon. It is there. Something's there, but we don't know what it is. So it's like the old question if a tree falls in the forest and no one is there, would it make a sound? Quantum mechanics would say that if the tree falls in the forest and there's no one there, you can't really say that there was a tree there at all. I mean, not only can you not know if it makes a sound, but you don't know that you can't know that there's a tree there. In fact, it's likely that there is no tree there.
Now, I know there's been a sort of classic critique of that idea that says, well, just because these things are true on a quantum level doesn't mean they're true on a macro level. That just because the observer has an effect on the quantum, particles doesn't mean that the moon isn't there when we're not looking at it. Now,
right.
You think that was a false critique, that the micro and the macro, that the same principles apply, that quantum principles are at play in the macro world? Is that what you're saying?
No, I understand the nature of the critique, and it's not completely wrong.
Okay.
But the fact is that the quantum world is not just the world of the microscopic.
Okay.
There are things that are macro in scale that are quantum and have been demonstrated in the laboratory. There are things even at the cosmological scale that are quantum. And in fact, as I think most physicists would agree, that there's no magic that happens between the quantum and the classical world. There's no discontinuity.
Okay.
It's just that the classical world is a good approximation. It's a special case of the quantum world. But anything that looks macro, or anything that is macro, ultimately is a quantum system. It's just an incredibly complicated quantum system that is so complicated that we can't write down an equation. But we all assume that any hunk of matter, even if it happens to be lots of hunks of matter all together and you call it a shoe, that's still a quantum object. The reason why it behaves in classical terms is because the statistics of the system are now large-scale statistics. It's like thermodynamics. And you can start to make predictions about how billions of individual particles behave in very, very stable ways. So there's a quantum probability that my shoe will just disappear the next instant. But we can predict that it probably won't happen in the lifetime of the universe because it has so much statistical stability in it because there's so many particles. Okay. The other thing that a classicist would say is that, is the moon really there when we don't look? Well, probably, because there's a lot of statistical stability in it. Nevertheless, we can't know that. I mean, as soon as we withdraw our attention to it, we know that with microscopic particles, that the particles are in an indeterminate state. In other words, it's not like we don't have knowledge of it. We don't know, but that the particles actually are not in a real state. They're in some abstract virtual state when they're not being looked at. And some physicists say that it might provide a boundary of what we can know, what is knowable. And that's why the epistemological issues are important there too. There may be a limit on what is knowable through our means of probing in the usual way, like physics experiments. Okay. So yes, there's. This is the same argument, by the way, that a neuroscientist would say that, well, we don't need quantum mechanics to understand the way a neuron works. Because a neuron is made up of trillions of individual particles, and by that time, it is so stable that we can understand it perfectly well in classical terms. At this point, it's not easy to say that that's wrong. Except, and the except I think is an important one, if they were wrong, and if, in fact, the bioentanglement was going on inside our brain and outside as well, as soon as that is a possibility, it opens the plausibility that when people talk about getting information at a distance, somehow transcending both time and space, which sounds a lot like psychic phenomena, that is exactly what a bioentangled brain would do. Okay. You see? So the argument here is it's a little bit like a push and pull. Okay, classical neuroscience does not need yet to consider quantum phenomena, although there are some who are talking about it. I mean, people like Stu Hameroff and folks like
Yeah.
that.